first of our two Suppliers technical sessions. And it is titled Leveraging Cloud and Model-Based Design for SDV Development. And we are joined by Luigi Milia, Automotive Industry Manager for EMEA of Mathworks. Over to you.
Thank you very much for the nice presentation. And so, yes, I think I can speak directly with our two folks here in the audience, but thanks for staying. Yes, so my name is Luigi. I'm part of a global team at Mathworks that work to, let's say, capture the industry trends and convey those trends internally to drive our automotive strategy. And before joining Mathworks, I spent 20 years in the industry working on powertrain control software development. Okay, so a few words about Mathworks. So we make MATLAB and Simulink. MATLAB is a computing platform for design algorithm, data analysis and visualization. And Simulink is a graphical environment for model-based design and simulation used to design and develop complex multi-domain systems. We are a global company. Our headquarters is in the US, near Boston in Natick. And we do have offices all over the world. And our office here in Italy is here in Torino. It's actually very close to where we are now. We are present in many different industries: aerospace and defense, industrial automation, semiconductor, telecommunication. But we do have a strong footprint in automotive, where, let's say, our solutions are broadly used by OEMs and suppliers to design and develop complex mechatronic systems. Okay, let's get to the agenda for today. I would like to talk about the buzzword of the hour in automotive, that is the software-defined vehicle, or SDV. So my presentation has actually two parts. On the first one, I will briefly introduce the SDV trends, highlighting the motivation behind it and its impact. And on the second part, I will share with you a concrete proof of concept that we developed together with Amazon Web Services, Electrobit, and Synopsys to show a possible workflow for, let's say, SDV development with model-based design and the cloud. Okay, let's start. And let me start with this quote for Mark Andreessen, a Silicon Valley innovator, back in 2010s. So essentially he said that in the future, every company will become a software company. And so if you take the largest bookstore, Amazon, so Amazon is actually a software company. If you take the largest video store, Netflix, so Netflix is actually a software company. So what about automotive? So fast forwards in the 2020s, so essentially each major player has announced an important software strategy. And if you look at this quote from Luca Di Meo, for example, he says that the software, electronics, and onboard intelligence will determine the value for the final customer. And I think that's a pretty, let's say, good definition of software-defined vehicle. So essentially there is this notion that the brand distinctive features and the main value for the final customer will come from the software. And yesterday, also in the panel discussion in the morning, this was brought up. And so for sure this is driven from customer expectations. So there is an expectation for clean and safe mobility, together with a sort of seamless digital experience from our smartphone to the car. And so these kind of expectations are actually quite demanding for the industry. So are quite demanding for new technologies and innovation. And of course there are a lot of investment that are going on in these technologies. And so the industry is also looking at this as essentially a new business opportunity. So there is the idea to actually make better profit margin for the industry by selling, for example, software services, application, subscription plans, and so on. Okay, let's say, keep the business motivation aside and have a look at some of the technology enablers for the software-defined vehicle. So essentially, the main point is the is that the auto industry really needs to be able to deliver much more software, complex software, much more quickly, ensuring the same level of quality and safety and security that the final customer will be expecting. And so a first enabler is, let's say, a new kind of electric and electronic architectures. So the electronic architectures in the car are now shifting towards centralized architecture with an high-performance central computer and with some, let's say, zone ECU controllers. So centralized architectures is one enabler. And then, of course, there is the software. So again, in order to be able to deliver more software in the car more frequently, is really required a new paradigm for the software architectures. And so this is where service-oriented architectures and technologies such as hypervisors come into play. And then, of course, connectivity. So this will be, of course, a must to enable over-the-air updates and also to leverage additional services provided by the cloud. And last but not least, safety and security will continue to be extremely important for the technology in the car. Okay, so we saw that there are new technology being developed right now, but it's not just about new technology, it's also really about new way of developing such systems. So also the way of working is actually changing. And so what we are seeing is that so the OEMs are bringing in-house more and more software development, and essentially this is, let's say, reshaping the relationship across the value chain. So we see that OEM work more and more closely with tier 2 supplier, with silicon supplier, for example. And there is also the need to, let's say, be quick, agile, and so there is the need for a new way to collaborate across engineering teams, and so leverage, let's say, more structured and sophisticated collaboration repositories. Yes, I was mentioning that the industry needs to be agile and deliver, let's say, software at speed, and so for sure there is a shift towards a more agile workflow, towards continuous integration and DevOps. And also, again, in order to be agile and quick, so the industry cannot afford to, let's say, test all this software on physical prototype, and so there is really a need to virtualize through simulation, so virtualize the development and virtualize the testing of this software. And last but not least, also there are emerging, let's say, new workflow that are leveraging the cloud, and also new applications such as digital twins, fleet analytics, scenario replays. All these, let's say, applications will be hosted in the cloud. And so what does it mean? So what are all these trends mean for model-based design? So model-based design has been quite successful in the automotive. It's a very well-established process that revolve around the notion of working with models. So you have models of the vehicle, model of the components, and you have model of the software that run that vehicle. And so with model-based design, you are able to continuously refine your models. So you go from the behavior to the implementation models, and then you go to the code. And thanks to simulation, you're actually able to iterate fast and refine and improve your design. So there is this notion that model-based design enable you to shift left, so essentially anticipate as early as possible the testing and validation activities to find defects earlier. So model-based design, very well established, but also it needs to evolve. So I think we are also working strongly to evolve model-based design to address the needs for software-defined vehicles. And so, for example, in addition to the established support that we have for traditional automotive electronic control units, we're also now addressing central and zonal architectures. And so we are supporting, for example, service-oriented architecture straight from Simulink. That is our environment to design the software. And then if we look at how developers used to work in the past. So they have their tools working on their desktop, and the design process was mainly interactive, so human-driven. And now there is also a shift towards moving the development tools in the cloud, towards, let's say, implement automation, continuous integration, and so. And then also, traditionally, those tool chains were managed by configuration system, and now there are, let's say, much more let's say, complex and modern structures to manage, let's say, complex software development. So we are working to, let's say, update model-based design with this additional capability. And so in the second part of this presentation, I will show you, let's say, a kind of concrete example about how we can use model-based design in the context of, let's say, an agile and fast development for a software-defined vehicle. So imagine that you are part of the software factory at your OEM of choice, and the marketing teams comes to you and say, look, we want to bring to the market a new feature. This is an electric vehicle. And so we want to bring to the market this feature that we call it Sport Plus that will, let's say, improve the acceleration while, let's say, keeping the battery range, still okay, right? Okay, so, and if you look at the architecture for this system, so we will have the infotainment, so the interface with the driver, and then in this case, we have two main electronic control unit. We have a central computer, an high-performance computer that is called the vehicle control unit, and then we have the battery management system that actually manage the behavior of the electric battery of the car. Okay, so this is our system for this example, and as you can see, actually it's a quite, let's say, complicated task. We have conflicting design goals. We have to deal with different kind of chip architectures, high-performance central computer, classical ECU. There are also different level of safety required, and of course there are multiple teams involved. So, and we have to, deliver this new functionality that doesn't require any change in the hardware, and also we have to deliver this new functionality quick and fast without having access to any physical prototype. So we have to essentially, work with virtual development. So how can we do that? So we're going to do that in, let's say, in 4 steps. So the first steps, we are going to leverage a system-level simulation. So we are going to leverage simulation to make a study of our system. And so here we have the challenges. So essentially,